Welcome back to Statistical Inference 5114. We're going to finish up our discussion of this uniform problem. That is not to say that you understand everything with this problem. So I've given a couple different statistics for estimating theta. I want to talk about this one last. But we have other statistics. We have theta hat is equal to maybe the maximum. Maybe some scale version of the maximum. So maybe n plus 1 over n times the maximum. This I call the Bayes estimator. Now, that's not to say that it has to be Bayesian to do this. We'll see later on in the class how I derive this. So I gave you a heads up to it, where we write down the likelihood function. We'll talk more about sampling distributions versus likelihoods as we go through this class. And then I told you which class of prior I used, and what I ended up doing with that prior is I chose a particular brand of the prior such that the estimator would be unbiased. So I invoked a criterion, and it told me how to come up with that prior. That's a very Bayesian thing to do. There's other things you can do. So we also looked at the range, xn minus x1. We looked at the mid-range times 2, xn plus x1. And this was the mid-range times 2. If I divide by 2, that's the mid-range. Multiply by 2, that's 2 times the mid-range. So lots of different estimators that we can write down. And they're all okay. Some are better than others. And this class is about discerning what criterions you want and what makes something better and how do you derive it. So this is all just kind of in idea land right now. There's lots of different contenders we could come up with, and some of them we prefer. So this whole discussion will be going on throughout the class. After we get done talking about this problem, I want to move on to independence versus exchangeability. This is not in the book, exchangeability, but I want to make a couple points about it. And then I give you a homework problem pertaining to it. Okay, let's talk about this. Question is how did I get it? So what we did to derive this least squares estimator is we solved this problem. So theta hat, least squares, is equal to the sum from I goes from 1 to n. Give myself a little bit more room right here. Xi, these are the order stacks, minus I over n times theta squared. I took the arg minimizer over theta. Let me just draw a picture real quick. So say I have some function, maybe as a function of theta. So the maximum for this function is right here. That's the max. This point right here, I'll make it a star. This is the argument that maximizes the function. So that's our notation if you haven't seen that before. We've all seen what it is to minimize something, but in this function, we want the argument that minimizes this. Turns out the solution to that problem is right here. So any one of you should be able to solve this. So how would you figure out this arg minimizer? What would you do? Procedurally. Take the derivative? Set it to 0. Yeah. And then you would have to convince yourself that the minimum doesn't wind up on the endpoints. So it could do that. How do we know that the minimum is not on the endpoints? And that Peter's solution will yield the right thing. How can you tell?
Isn't it because when you sample in a uniform, the
maybe I think about it a little bit differently. This would be true regardless of how I sample it. So I think it's true regardless of what that distribution is. So I'm not saying that it would give you a very good estimator. So there's a reason we picked this thing, and that has to do with the uniformity of everything. But this function right here, regardless of what the input's in, I know that the minimizers don't live on the endpoints, irregardless of the sampling distribution. How do you tell? Okay, I will write down a word for you. This thing is convex. So if you've ever taken an optimization class, you like convex functions. So that means once they start going down, they keep doing that. They don't come back around. They don't have two bumps in them. That's a parabola. And so this is a quadratic function. Convex, it's a parabola. So I know there's only one minimizer to it. So if you have convex functions, only one minimizer or one maximizer. So that's very nice. In general, for complicated problems, you don't really know. You have to check a lot of things. There might be a whole bunch of different minima, local minima. But for convex functions, local minima are global minima. That's good. So that's all I'm thinking about. So good. Stephen's absolutely right. That's what you would do to solve this problem. Does this solution look familiar to anybody? Let's look at a slightly different problem. Just for some motivation. So I'll switch my problem a little bit. You ever seen this? I got rid of these. Ever seen a problem that looks like this? Our minimizer over some parameter, I'm going to call him beta. I goes from 1 to n, yi minus xi transpose beta squared. So this is a vector right here. This is a vector moving in that direction. This right here is just an individual data point. So this right here is a vector moving in that direction. So all my vectors are always called vectors because that's what we like. So this is a row vector. Anybody ever seen a problem like this before? Bunker.
Is that just the linear regression?
Yeah, this is a regression problem. So this is the typical least squares sort of problem. So this is what we do in regression. So a lot of times we have models and we say yi is distributed normally with some mean and some variance. So standard sort of regression problem right here, where this is a vector of inputs. And beta are your coefficients in a regression model. So this is simple linear regression. I should say multiple linear regression. But it's just linear regression. I don't like to write it out this way. I like to write it a little bit differently. So this problem, this thing right here, I could write a little bit different. I could write this out as y minus x beta transpose y minus x beta. So that sum can be written in matrix notation. This thing right here would be the y's. This thing right here would be a vector of all of your x's. So this would be a matrix of all of these things. So this would be x1, x2, all the way to xn. The covariance that you measure when you're trying to predict y's. And then this beta right here would be the dimensionality of the problem. Whatever the length of these are, so let's just say this is p-dimensional, then the betas would just be this class, you've seen the solution to this. So I got to see this from a lot of different vantages when I was an undergrad. And then I was really impressed when I was able to take this derivative. Of course, taking it like this is a mess. But working with this function right here is a lot easier. So I'd say brush up on your linear algebra. Think about how you take derivatives with respect to vectors. But this problem has a solution. So if I write it out in terms of a vector of y's, this thing, a matrix of x's, then I can solve this problem really easily. Does anybody know what the solution is? Bonker.
Isn't it x transpose x inverse times x transpose y?
That's it. So we should all know that at any time somebody wakes you up at 4 o'clock in the morning and says, I need the solution to this. You say exactly what Bonker just said. So this solution right here, we'd call this beta hat because it's an estimate. This is x transpose x inverse x transpose y. Of course, we need to make sure that this inverse exists, and there's a number of things that you could do to the x's so that that is not invertible. So if the x's are multi-collinear or p is greater than n, you won't be able to invert everything. So hopefully you've learned that before. How do we do this? All we do is we take a derivative over this function. With respect to betas, we set it all equal to 0. We get that. You're going to see this problem a number of times in this class. You'll derive that for yourself. If you want to derive it right now, you probably could figure it out. So, but we'll be going through this, and it shows up in a number of problems, number of contexts. Bayesians use this answer. A lot of times they cut priors on beta that are flat, proportional to 1, and they would come up with this solution as well. If you weren't even into modeling and you didn't think about this as distributional, you could just solve this optimization problem. It shows up right there. If I use this form of the problem, I could write down the likelihood function for betas and maximize those, and you would come up with that solution as well. So a lot of different ways to come up with the same solution. Lots of different methodologies for coming up with it. All this really is doing is it's figuring out the best fit in some sense. The best fit in the sense of squared error differences. And if I change that norm, I change the problem. And they'll have a different solution. But a lot of people will go running off for this solution. It's one of the easiest things you can do. We sometimes like these squared norm functions because they're smooth, and we can do calculus. If I change the problem and I cut absolute values over here, I can't do calculus anymore. I need a different mathematical technique to solve the problem. We'll leave it simple right now. But if I ended up writing down that these were my y's, if I change this problem, it looks very similar, and I just write down, this is the ordered data points that I've seen. So I flip my notation around, my x's are now my y. This thing right here would look like the beta, but it's just one-dimensional. So this is just 1D. Whereas this problem right here was a little bit harder because beta was p-dimensional. Hopefully this is ringing some bells for you. And this right here, these would be my new x's right here. So if I wrote down x was equal to just this vector, 1 over n, all the way down to 1. So just to be clear, this is 2 over n, 3 over n, so on and so forth, until I get n over n. So if I re-encoded the problem like this, I could look at this solution and figure out what it is. So keep in mind, my x is one-dimensional in this. And so this is taking the place of x transpose x inverse. That's what that is. So I can divide by it because it's scaling. If you ever in this class divide by a matrix, I'm going to freak out. So don't do that. Okay.
Why did you set y equal to x1 to xn?
just because I'm reinterpreting this problem right here. So now I'm not thinking about that. I'm just writing this down with some different notation.
Oh, okay.
So this right here and everything, so this is kind of taking the place of my X transpose X inverse. This right here, these are my X transpose, if you will, and those are my Y's.
Oh, okay.
So this solution that we just wrote down, this part is the numerator. This part is our denominator. So I can solve the problem exactly the same. My point is that if you did know the solution to the regression problem, that solution jumps right out at you. Please.
Why don't you choose another X? Why this?
I'm just matching notation. This is just a notational thing.
I mean, I overlooked. Why do you choose that?
Oh, okay. You want me to discuss why I did this? Yeah, good question. I want to discuss that. So, the point is, again, there's lots of techniques for solving the problem. Let's just look at this right here. I over n theta. Why am I matching those? I'm trying to make these as close as possible to each other by budging theta around. If I make these really small on average, then this sum is going to be small on average. So think about the problem. So this is going to be 0. This is theta. We're sampling uniformly from everything. This point right here is going to be x1. This point will be x2, whatever I got, the second biggest value. Try not to make too much of a mess out of my graph. There'll be some points over here. This one's the maximal value. Xn. Let me just ask the question. How big do I expect this interval to be? The gap between 0 and my first order stack.
1 over n?
Yeah, 1 over n times theta. So that's where I expect that to be. So this is going to be about close to theta over n. Would be that point. What do I expect that to be close to? They're not going to be exactly, because this is random data. I expect it to be 2 over n times theta. So I'm just chalking up the interval into quantiles. And so these right here are my empirical quantiles, what I observed. It's uniform, so I know that those are actually quantiles. Those are my empirical ones. These are my theoretical quantiles. So I'm trying to match them close to each other. I know that Xn, technical difficulty over here. I know that Xn is close to theta. And that's what this says as well. Let me fix this. Still getting used to it a bit. So that's why we picked that. So I was mistaken. I went back and I watched my video from last year when I taught this. And a physicist had introduced this. He was thinking about, well, if Xn, the maximum, is a good estimator of theta, I should be able to use all that other data to estimate theta. Because I know a relationship between x1 and theta. I know that it's about theta over n. And x2 is 2 over n times theta, about. And so I thought it was interesting enough that I coded it up and looked at its performance. I knew something beforehand. I knew it wouldn't help. So if you think about this solution right here, there's a lot of variability in this thing. So if I just looked at the variance of this estimator, I would have a lot of variability coming from this multiplier. And I have inherent variability from the order statistics as well. So I'm introducing a lot of variability into the problem, stuff that I don't actually need. I want to just point this out. If we look at the likelihood function, I wrote this down last time. Somebody asked me about this. So I want to be clear about it because this problem will keep coming up. So our likelihood, given all of my data, I'll say x1 to xn. You could condition on the order statistics if you wanted to. But this likelihood how do we get it? We write down the joint sampling distribution and then we change our perspective. So we write down the joint sampling distribution. So I'll say to derive. We end up writing down the joint sampler. And that's just going to be the product. I goes from 1 to n of all of my fxi's given theta. So what is this thing? I should be a little bit careful with it. You might say it's 1 over theta. So the PDF that we've been playing around with is 1 over theta. This ends at theta. We see all our data points in this interval. So we might be inclined to just write that down. If somebody wrote this down, I would be utterly confused if I were staring at it. If somebody were telling me that's the likelihood function. So what you usually do is you write down the joint sampling distribution, and then you plug in all your data into the equation and you let beta be variable. That's what a likelihood is. So it has the same mathematical form as the sampling distribution. The x's are random variables in that equation, if theta is fixed. But if I plug the x's in and I fix the x's, then theta will be variable. You can't say it's a random variable yet, because it doesn't have that property. What's wrong with this? So if I wrote this down, I would get 1 over theta to the n. And that's not a likelihood. How can you tell?
We have the range.
Say what?
We have the range of x.
Yeah, where's
From
the x's?
0 to theta.
Exactly. Where are the x's? So the likelihood is telling us a function that connects the data to the parameters. So this isn't right here. What we need to do is we need to fix this up by multiplying by our constraint. The x's are always less than theta. So x's, xi's, always less than theta. So I need to write in my delta function right here. I'll just write down, this is going to be the delta function that xi is less than or equal to theta. And that's really showing the whole relationship between the data and theta. I can write this down that if I have the product of all the xi's being less than theta, I can write this more simply. That this would just be the maximum is less than theta. If I've actually encoded everything correctly, I know that xn minus 1, the second largest number, is less than this right here. So I don't have to write all those down. Here's my point. When I write down the likelihood function, I stare at this, I plug in all of my data. My real relationship is just right here. xn is less than theta. This is the maximum value. We're going to learn a principle in chapter 6 called the sufficiency principle. And if you're a stats major, you already know this. That this is as much information in the sample as the whole original data set. That has all the info in it. And I'll explain that once we get into chapter 6. But the likelihood function only depends on the max. We'll look at this later. We're going to keep coming back around. But what that tells me as a statistician is all you need is the maximum. And if you use anything else, you'll just get a worse answer. keep in mind we need all of the data points to figure out what the max is. So we are using all of the data when we order everything. But once we've done that, we only have to hold on to the max. So I haven't explained this very well, but at least hopefully I've motivated that maybe this answer isn't going to be so great because it depends on more than just the maximum. It depends on all of these order stats, which is only introducing variability into the problem. So we're not there yet to understand completely why you just need to use the maximum, but at least we're starting to get an idea. What I'd like to do is just simulate some of this for you. So somebody asked me during one of our Zoom sessions if I could explain the code real quick. I'll try. So I gave you a piece of code. It's got whatever the maximum value is. Right here is an input. I called it A in my code because I didn't want to write theta. So I'm just going to change that to A. Then I talk about the number of samples that I'm going to play around with, and I can keep changing these numbers. And then I say how many times I want to repeat this process. So I'm going to empirically just kind of generate data and then see how well it works. And I'm going to compare all the estimators. I don't want to do it just once. I want to do it over and over and over again. If some estimator is better than another one, it might just be by chance. On average, the direction might go the other way. So I'm going to repeat this process a whole bunch of times. Now 1,000 isn't a whole bunch of times. So nowadays we can do things like putting in 10,000. No big deal. We can store even more than that. Usually you want to crank that up really high. Repeat that process over and over again. I'm going to talk more about this next time when we discuss bootstrapping. But if I were, if I could have anything in the scientific world, it's that I could just crank that number up arbitrarily high and have that much data. The trouble is you can't, because data is really expensive. But on a computer, it's really cheap, because it's synthetic. Okay, so what I'm going to do is I'm going to generate my data points. So rand is the uniform random number generator. What I'm asking for is a vector of n of those, and I'm multiplying it by a. I'm just scaling it to that interval length. So rand is a uniform between 0 and 1. It invokes the Mersenne twister, if you want to know what it's actually doing. So that's the generator of choice in both R and MATLAB. It's kind of your best uniform generator. We didn't need to know that, we just need to know the command. And then I write down a whole bunch of different test statistics. The mean, X bar, we looked at that. We looked at the range, mid-range times 2. This is my least squares estimator. So somebody asked me, what does lim space mean? What is that function? Here's how you figure it out. You cut and paste it. I go to my window right here. I need to say something about what n is. I'll say it's 20. Then I just type that command in. And you just look at it. So I go to my command window and I just look at what lim space is. What it's done is it's just created a vector that looks like that. So it's just 1 over n, 2 over n, 3 over n, and I invoke a function to do that. So if you ever have somebody's code and you want to know what is it doing, you do the same thing everybody else does. And you dissect it, and you just print out what that line did. And then you'll know. Or you can type in help into the command window, and it'll give you a help box. So those are just my weights. So this estimator is the same thing that is what we wrote down right here. That's how I got that. I guess Peter's been kind enough to code this all up in R for everybody. So did you end up getting that from board?
I haven't been working on that one.
Fair enough. You don't really need to. So it's a bad estimator anyway. So I'll demonstrate it. Everything else is just print commands. Prints to the screen and then some plotting. So I'm going to just go through this real quick. Let's just see how well it works. Range, mid-range. my problem. Okay, so I've got now 10,000 samples. I did plot for us what the mid-range looks like next to the range. They're related to each other. So, and there's these strong diagonal lines moving through everything. I want you to think about that a little bit. So there's a problem in the book that addresses this and mathematically derives that for us. So we could also do that without simulation. We could do it mathematically. But that's kind of cool. Just a prelude. Here's what I really want to show you is the different results. So what I did for each one of these methods, I guess I looked at the range, 2 times the mid-range, x bar, 2 times x bar, my least squares estimator, and then my phase estimator. I could change that phase estimator around if I wanted to invoke a different property. The prior that I used ends up making everything unbiased. But it creates a little bit too much variance, and there's a trade-off there. You can make this lower MSE if you wanted to. So, and I showed you what that estimator would look like. So this one down here, where I look at n plus 2 divided by n plus 1, and I multiply by the max, that's actually better in terms of mean squared error. We could derive that up front. So take a little bit of calculus, but you could do it, and by the end of this class, you'll all be able to do it. So what I did is I just plotted what my different estimators were. So I just made a histogram of them. And I can kind of get an idea of how these different estimators are performing. So the range is always to the left of my maximum. My maximum in this problem was 10. So my estimates are always to the left of 10. Because I take my maximum and I subtract off my minimum. This answer looks a little bit more appealing. I would say if I only could choose one of the 2 estimators, either the range or 2 times the mid-range, I would take 2 times the mid-range. So just because it flanks 10, it can be on the right-hand side of it and it can be on the left-hand side of it. You usually get better properties when you're not just shoved up against a boundary. 2 times x bar, it's okay. There's a lot of variance in here. There's much more variance here than there is here. So x bar, we sometimes like. Somebody help me out and tell me why we like x bar a lot. It's unbiased, yeah. So 2 times x bar is unbiased. So that is a reason.
Isn't the variance usually lower than just using a single observation?
Yeah, so the variance gets small, quick, maybe. So something to do with variance.
So this means that it's mostly efficient estimator.
It's not in this case, but for some problems it is. For this problem, it's not even close. But in a lot of problems it is. So if we were estimating mu in a normal distribution, yes. In that case it is. But it's problem specific. I like x bar because of the central limit theorem. That's usually what I like most about it, is I know how it's distributed regardless of what the underlying distribution is. That's almost a true statement. It's almost normally distributed depending on what it is. And so I like that property. That's kind of cool. We'll get into that. I think that's 5.3 or 5.4 if you want to read through that. We'll be seeing it. It's also on our cover slide from the Lehman lectures. That's on the chalkboard, the central limit theorem. That's what we're talking about there. So saying that, even though it has some appealing properties, it's not our best answer. And here's the other ones. What I ended up doing is I plotted the mean squared error. So MSE is just this. This is going to be my theta hat I minus true theta. squared divided by n. Oops, not n. This will be, I'm going to say r. R goes from 1 to cap r, divided by cap r. So cap r is my number of replicates. So that was my number of times that I ran this thing. That's 10,000 in the code that we just ran. So it looked at 10,000 different instances of collecting 20 data points. I look at how well my estimator compares to the truth. This is my estimator, or I should say my estimate, and this is the truth. So in a simulation study, I can generate from the truth, and then I can compare my answers to the truth. We would love to be able to do that in the real world, but if someone gave you the truth, you would just use it. You wouldn't estimate anything. So this is a theoretical thing. Problems like this, right here, I can analyze how well different procedures work through the simulation study, but it's because I get to generate from the truth. If I found an estimator that worked really well, beat everything else on average, maybe that's my criterion, then I might use that estimator to solve problems that look like this. Now, I've got to admit, nobody's ever come into my office and said, I need a solution to this particular problem. It's a little bit simple. So, there needs to be at least 2 parameters in there before you can come to my office. Okay. So, here's what it looked like. So, I looked at the MSE for these different estimators, and you notice that the Bayes estimator, or the scaled maximum, however you want to think about it, is performing better than the other stuff on average. Quite dramatically. The quantile least squares estimator, it's not the worst one in the catalog. The range isn't too good, and 2 times the mean isn't too good. So saying that, 2 times the mid-range is all right. But it's not as good as this other thing. So in this class, we might say the word optimal a lot, but it's always under some assumption. We know the model. We know what's going on. In the real world, we don't get optimality because everything's an approximation anyway. So our models are approximate. We make them up. We check to see how well they're working. This class is going to help you to not make bad decisions, so I would say. So you might invoke some criterion, an optimality criterion. You're going to say it's optimal under this thing that I've chosen. So that's an assumption. But this class will help you to pick estimators that are pretty good. If you did know the model, in reality, you could come up with something that was optimal so long as you came up with the criteria right here. So this is my measuring device. If I were in a Kaggle competition or something like that, or doing some predictive analytics, and they told me how they were going to score us, I would build my answer to optimize that score. I would pay attention to it. Okay. We could change these answers a little bit. So I will kind of say there is a trade-off between the interval length and n. So if I make the interval length really big, 100, 20 data points isn't very good. And my errors would go up. There's my answers. Here's MSE again. So if I increased everything, increased A, basically I just took 20 data points and I'm trying to fill out that space so I can learn about it, but it's not going to perform as well, just because now it's much more sparse. So bigger spaces with more sparsity in it requires more data to learn about that space. So how many data points would I need to do well? Well, you have to tell me what the criterion is. But if you said I need my MSE to be particularly low, then I can answer that question and tell you how many data points you would need. So you can play around with that code just to kind of get a feeling for things, but I switch the page unless there's any questions. Been talking about this problem now for like 3 or 4 days. So all motivation. Okay, cool. So I want to move on to exchangeability versus independence. Let me give myself some room. Somebody help me out with this. What does that mean? You've been taking math and stat courses for a while now. Everybody kind of knows what it means. Somebody tell me in plain English, what is independence?
One change, the other not change.
One changes and the other not change?
I think so.
I can kind of understand what you're saying, but I think what you maybe mean to say is one thing doesn't influence the other.
Yes.
Okay, because things are random, so everything's changing all the time. There was another answer? Yeah, please.
Joint densities can be expressed as marginal densities.
What's that? Oh,
Yeah.
the density is factorized. Is that right?
Yeah.
So that's pretty good. Kind of like that. So the one thing doesn't affect the other. One random variable doesn't influence the other. I kind of like this. It's not what we mean, per se, by independence. There's more to it. That factorization of the densities is the mathematical way you would say it. So I like that because that's true. So the density is factorized. But I wouldn't tell somebody that if I were a part. So let's see if we got another. Anybody else want to take a whack at this? What's independence in plain English? Hard to think about. So let me just ask you, is this true? So let's just say I have some problem. Xi is coming from some function. I'll say it's got some parameter in there. We'll let this be IID. So this is the independent part, identically distributed. Every time I sample, I'm not going to change the distribution. I'm going to do this 2 times. 2's enough, of course. Make it real simple. Is this true? These are my draws, my instances. Unfortunately, I don't get an opportunity in this class to call you up to the board, but normally I would say somebody come to the board to write down what independence is. Who would have written that down? Quite a few people. That's usually what happens. People will write this down. This turns out to not be true. So that's not what independence means. Rather, what we mean is this. You might say to me, hey, that's what I thought. You know, you're just using some notation. I didn't know what you meant. But I want to be really clear about this. This is true. That's conditional independence. So you have to condition on the parameter. This only factorizes if you know theta. So I want to be really clear about that. So this is marginal independence, and it's not true. So things don't factorize marginally. So marginal independence. And if you were in a math class and you were doing set theory, this is okay. If those were sets, I've got no problem with that. But this is stats class. This is inference class, so it's all about theta, knowing theta. So this, I would say, is conditional independence. So where we're conditioning on theta itself. So conditioning on theta. I'll try to make my point in a simulation in a moment. It's not a difficult concept to understand, but it does seem to me after teaching this for the last 8 years, most people don't give this too much thought. I think it's important. So, we just ask, is this true? X2 given X1 is equal to X2. When I write it down this way, if this was true, I'd be inclined to think you don't learn about X2 through X1. X1 doesn't tell you anything about X2. Is that statement true?
Yeah.
So, same exact point that I'm going to make. I'm going to say no. So I'm going to say under this setup right here, it's not true. Although it seems like it should be true. So this is not true. But this is true. Fx2 given x1 and theta is equal to fx2 given theta. That's true. If they're independent. But what I really mean when I say independent is I mean conditional on knowing theta. So if I knew theta, then I don't learn through the data. But if we just think about this for a moment, we have to be learning through the data. So otherwise, if I had independent data out there, if this original statement was true, it's telling you that you can't learn anything by looking at old data. What you're actually learning about when you're looking at data, you're learning about theta. So you're inferring, and that tells you about future data. So let me just do a quick experiment. Well, let's just start up next time with it. I think we just ran out of time. So 9:55. This is a 50-minute class, right? Okay. So I'm going to come back next time and I'm going to try to exemplify this point to you. But basically, I'll just give you a quick analogy. If I'm thinking about somebody maybe shooting at the free throw line, some basketball, and I believe maybe that this person had a random number generator and they always threw the ball in exactly the same way. The question is could I learn anything by watching them throw the ball? And in reality, you can. So what you're doing is figuring out what their probability is of hitting the basket. And the previous data tells you that. So let me come in next time, exemplify what I'm saying right here through a simulation, and then I'm going to tell you about another concept called exchangeability. The difference is independence is a model-based thing. It's not a statement about data. It's a statement about the data when you have the model. But exchangeability is a statement about being able to shuffle the data. And so it's something that happens irregardless of model. So it's a data quality versus data width quality. Let's pick up next time and I'll try to clear up all that confusion. Thanks, you guys.